Welcome back to Calculus 3. This is section 13.3 with polar coordinates. This is the example. This is part 2 of 2. If you haven't watched the first video on the theory, I'd suggest you do that. So for this first example, let's look at the double integral from -1 to 1, from negative square root of 1 minus x squared to positive square root of 1 minus x squared of the surface 2 divided by 1 plus x squared plus y squared, quantity squared, with respect to y first, then with respect to x. If we're considering what the surface looks like, let's just write down our bounds first. So we know that x is an element of -1 to 1, so x is our constant bounds, and y varies between negative square root of 1 minus x squared to positive square root of 1 minus x squared. And so if you don't recognize already what the y bounds look like, we can say that if y equals negative square root of 1 minus x squared, we can rewrite this as y squared by squaring both sides as 1 minus x squared, move the x squared over, and we see that we have x squared plus y squared equals 1, which is a circle with radius 1. So knowing that the y is a circle, so we have the upper and the lower bounds for a circle, we can start to get an idea of what our area looks like. So this is our upper curve for y. This is our y upper, square root of 1 minus x squared equals y. And this is our lower curve for y. Negative square root of 1 minus x squared. And then we have our x bounds as 1 and -1. So our region, in fact, is the entire circle with radius 1. So this is handy, because if the region is a circle with radius 1, then we know in polar coordinates our r varies, our radius varies from 0 to 1, starts at the origin. We think about what our ray looks like. A typical ray starts at the origin and it shoots out to the edge of the circle with radius 1, and our angle theta starts at 0 and it wraps around to 2 pi. So our angle starts at 0 and it wraps around 2 pi. So this piece is nice because now we can rewrite our integral as the integral from 0 to 2 pi, from 0 to 1. Remember, theta is on the outside and r is on the inside. 2 divided by 1 plus r squared, because x squared plus y squared equals r squared, and then the Jacobian dr d theta. Again, x squared plus y squared equals r squared as part of our properties for polar coordinates. This is our transformation. And our Jacobian is r dr d theta. To solve this integral, we can see that this is a nice u substitution. Let me just move this other problem down for a moment. So when we solve this integral, we see that the inner part of the integral, 0 to 1 of 2 over 1 plus r squared, quantity squared times r dr, if we let u equal 1 plus r squared, du is equal to 2r dr. So 1/2 du is equal to r dr. So the inside of the integral becomes 1 over u squared du. Notice the 2 and the 1/2 cancel each other out. So this becomes -1 over u, which becomes -1 over 1 plus r squared, evaluated from 0 to 1, which when we use the fundamental theorem of calculus, this becomes -1 over 2 minus -1, which becomes positive 1/2. So that's the inner integral. So the outer integral, again, let me move this problem down. The outer integral would then be from 0 to 2 pi, 1/2 times d theta. Again, you substitute in the 1/2 where the integral was, and then we get 1/2 theta evaluated from 0 to 2 pi. So we get the value of pi as our result here. So that is the value of this integral. So notice with this problem, we made several substitutions. We first drew our region, realized that it was a circle with radius 1, so that made our conversion to polar coordinates easy. As indicated over here in the red, we saw that we had to use our definition of polar coordinates, such that x squared plus y squared equals r squared, and recalling the Jacobian. We did a u substitution for our inner integral, and then made a nice substitution for the outer integral. So with our next problem, what we can do is we can see that our bounds on y look slightly different. They don't start at 0, like in our previous problems, they start at x. So when we look at our integral for this, our region, r, we're drawing our bounds. Our x starts at 0 and ends at 1. And our y starts with the function y equals x. This is a line y equals x. This is a line 1. And y equals the circle, the upper part of the circle, 2 minus x squared. So this is equivalent to the function x squared plus y squared equals 2. And this is a circle with radius square root of 2. So if I'm looking at the line 1, the circle goes through here where it intersects the axes at root 2 in both places. This is not exactly drawn to scale, so let's give it a little bit more curve here. So, and if our lower bound for our rectangles are y equals x, and our upper bound for our rectangles are y equals the upper part of the circle, then our rectangles look something like this. And our bounds for our a to b are from 0 to 1. So this is our region, this kind of upper slice of the pie. So as we're trying to determine what the value of our r and theta is, we need to determine aspects of our circle. So there's some key points that we know. We know that this looks like a segment on a circle. So when we're considering our conversion to polar coordinates, we need to consider how our radius and our angle are being considered. So our radius here starts at 0 because we have our ray, a typical ray, starting at the origin. So as we extend our ray out from the origin, we know our radius is constant. So we also know we're on the edge of a circle with radius square root of 2. So as we sweep through the circle, we always are going to square root of 2. So our maximum radius is square root of 2. Now our theta, when we're considering what our value of theta is, we need to consider what our angle is. So at y equals x, this is the same thing as saying that r sine of theta is equal to r cosine of theta by definition of polar coordinates. So at y equals x, if we take r sine of theta equals r cosine of theta, divide both sines by r cosine theta, we know, aside from the origin, that r is not equal to 0, cosine of theta is not equal to 0. We would get sine over cosine is equal to 1. So the places where tangent of theta is equal to 1 in this first quadrant implies that theta equals pi over 4. So that means that our angle has to start at pi over 4. And now for our starting angle, when we think about our diagram here, our starting angle is pi over 4, and it has to go up to the y-axis, which is pi over 2. So our theta value here, so here in red, theta has to go pi over 4, and then pi over 2 for the y-axis. We can also check that if we look at x equals 0, this implies that our cosine theta equals 0, which implies that cosine of theta equals 0, which implies that theta equals pi over 2. This is our finish angle. So now when we're solving this function, or excuse me, this integral, we're looking at the integral from from pi over 4 to pi over 2. And then the integral from 0 to root 2. Our integrand was 1, so we just substitute in our Jacobian, r dr d theta. Again, we keep our Jacobian together. And then evaluating this integral, we see that we have pi over 4 to pi over 2 of r squared over 2 evaluated from 0 to root 2. So root 2 squared is 2 over 2, which is 1. So we have the integral from pi over 4 to pi over 2 of 1 d theta. This gives us pi over 2 minus pi over 4 for a total area of pi over 4. And this is what we would expect if we did geometry to figure out the area of an eighth of a circle, which is what is represented by this segment. If y equals x divides the first quadrant of a circle in half, then we're looking at an eighth of a circle. If the total area of the circle works out with radius square root 2, then we would expect the area of that eighth of the circle to be pi over 4. Now lastly, let's look at a problem where we're sketching a region and setting up an integral, but not actually solving the equation. So with this particular problem, let's suppose we had d, instead of d area, let's do dy dx. So if we had an integral where we were looking at setting up the integral from 1 to 2 of the integral from 0 to square root 2x minus x squared of the surface with height 1 with respect to y, then respect to x. Let's think about what this region looks like. X varies from 1 to 2, and y varies from 0 to root 2x minus x squared. As you can see, this is not the same square root function that we've been dealing with earlier. So let's take a look at this. So y equals square root of 2x minus x squared. Square both sides. Y squared is equal to 2x minus x squared. Move things over. So x squared minus 2x plus y squared equals 0. So this looks like it has components of a circle, but isn't quite there yet. If you remember from perhaps your algebra days, we can complete the square on this because we have components of our squared terms here. So if we complete the square, we're looking to figure out what we can add and subtract. So if I subtract 1 rather, and then I add 1, what we can have is then we can turn it into x minus 1 quantity squared plus 1, minus 1, plus y squared equals 0, which looks like x minus 1 quantity squared plus y squared equals 1. This is now a circle with radius 1, centered at, not at the origin, but it's now centered at the value 1, 0. So we've shifted our circle over to the right 1 unit, and completing the square has helped us see that. You can also do this by substituting values in for x and y and determining what the values would be for the intersection of the circle. However, completing the square allows you to see that A, it is a circle and not an ellipse, and B, what the origin, or excuse me, what the center of the circle is. So in the image that we have, so now we know our circle has radius 1, it's centered at 1, 0. It's got radius 1, that means that we know its intersection points at 2, 0 and at 0, 0. So this is our nice circle. We know our x bounds start at 1 and go up to 2. Our y bounds start at 0 and go up to the top part of the circle. So our radius, or rather our region, is this enclosed red area with a rectangle indicated as such vertically. So when we're trying to determine how to convert this quarter of a circle into polar coordinates, we have to remember that our radius here starts at the origin in polar coordinates. So no longer does r in our polar coordinates start at 0. Our radius has to start at some value where it intersects the edge of our initial region before we can start generating our particular ray. So we can't start our radius at 0. We have to start our radius at some other value to indicate where we're starting the edge of our circle. So to do this, let's consider the fact that when we were solving for our y squared equals 2x minus x squared, this is equivalent to saying x squared plus y squared is equal to 2x. So when we were solving for our upper curve here, y squared equals 2x minus x squared, when we're looking for the upper part of the radius, x squared plus y squared is equal to r squared by definition of polar coordinates, and x is equal to r cosine theta, also by definition of polar coordinates. So dividing both sides by r, because we know our radius is not 0 at that point, we have r is equal to 2 cosine theta. This is our upper bound on r. Now our lower bound on r, if we have that we know that x equals 1 as our lower edge here in our image, we have the lower bound that x equals 1 is this line, then this means that 1 is equal to r cosine theta. So this means that dividing both sides by cosine, r is equal to secant theta. This is the lower bound. So now r is a function of theta rather than a constant. So before, in problems that we've worked on, r was a constant value for its bounds, but now r is a function of theta. So r goes from secant of theta to 2 cosine of theta. It's completely allowable for the functions to be, for r to be a function of theta. So as we go through this problem, we've found our bounds for r, so now we need to determine the bounds for theta. So theta starts obviously at the origin. If we're thinking about our rotation, or excuse me, starts at 0. So we think about our rotation along along the x-axis. That's where y equals 0. So for theta, if we consider along the line y equals 0, we have r sine of theta equals 0. and this implies that theta has to equal 0. This is our lower bound. Now, looking at our image, our upper bound of theta is when the angle gets to the point where the ray touches this upper value here. And so we're considering the point at the top of the circle. This value here is the value 1, 1. Our circle has radius 1. We're entirely at a height 1, 1. So this is the line y equals x. As we saw in the previous problem, the line y equals x is at the angle pi over 4. So at the point that the two curves intersect, we can even verify this analytically. We consider where x equals 1 intersects y squared equals 2x minus x squared. We're considering where y squared equals 2x minus x squared intersects x equals 1. That's at that point of intersection. We see that y squared is equal to 2 minus 1 equals 1. Using polar coordinates, we see that r squared sine squared theta equals 1. So we get that sine squared theta equals 1 over r squared. Excuse me, so at this point, rather, we know that the r will be this is one way to go about it. So this does require more preciseness on r. So an easier way is to consider the line y equals x as the intersection point. We do know information about the problem. We know it's a circle. And so at y equals x, theta has to equal pi over 4, as I said before. And that's our upper bound. So combining all this information between our lower bound and our upper bound, we have that our problem converts. Theta goes from 0 to pi over 4. R goes from secant of theta to 2 cosine of theta. We maintain our inner function, which if we recall from the beginning of the problem is just 1. And then our Jacobian, r dr d theta. And now we've set up the problem. And if we're asked, we could continue the problem from here. But in this case, we were just asked to start the problem. So as always, if you have any questions, feel free to email me and we'll go from there.